Hi, everyone. So the first talk this year is going to be by Gauri Joshi. So I'm really happy that she will be giving the first talk in 2019. And it's going to be on slowest gradient can win the race, error-runtime trade-off and distributed SGD. So Gauri, I'm really happy that you're going to give the talk, and I'll give you the stage, the virtual stage.
Thank you so much, Salim, for the invitation. As I was saying, this is such a unique and interesting way to host a seminar series, and I'm very excited to be a part of it. So maybe I can start by sharing my slides. Now you can see infinitely many copies of me. Can everyone see my slides now?
Yeah, I think if you can, yeah, we can, but maybe if you can maximize.
Yeah, go with like a full screen or with the slide.
Oh, okay. I think I thought I did that. Okay, I think now it should work.
Yes, now it's good.
Very good. So thank you for the invitation again. As Salim mentioned, the title of this talk is Slow and Stale Gradients Can Win the Race. So at least I want to convey to you what this race is and why this is an interesting race to participate in and try to optimize stochastic gradient descent. The work that I'm going to present today is joint work mainly with two students at CMU, Sanghamitra Datta. She is advised by Pulkit Grover, but she interned with me at IBM Research, where I was working before I joined CMU. And the other student who worked on this project is Jianyu Wang, who is my PhD student. And we also collaborated with several people at IBM, including Soumyadeep Ghosh, Parijat Dubey, and Priya Nagpurkar, who are co-authors on the paper with Sanghamitra. And as the title suggests, this talk is about stochastic gradient descent. So first, I want to actually talk about why this is an interesting and important problem to consider. The reason is that stochastic gradient descent, as many of you know, is the backbone of machine learning systems today. For example, the backpropagation algorithm, which is used in neural networks, is a special case of stochastic gradient descent. It's also used in reinforcement learning and many other machine learning systems. So because of this ubiquitous nature of SGD, speeding up its convergence is a problem of critical importance. It's like the one ring to rule them all, or the one problem to rule them all. And that is why it's of interest to many people, including us. So defining it more concretely, SGD at its core is where we are trying to optimize an objective function. Let's call it f of w. So we have this objective function that looks like what's given in the picture. And SGD starts at some point on this objective function and then takes small steps in the direction of steepest descent. And in machine learning applications, this objective function typically takes the form of what is called the empirical risk function, which can be expressed as shown over here. So f of w is the average of the loss incurred at each of n data points. So if your data set has capital N data points, then these small f represent the quality of the model. So a larger value of f means that the model, which is the w vector, is not as accurate. And that's why we want to minimize the average of these losses over the whole training data set. Okay, and the capital W, not the capital W, I mean the bold W that I have here represents the parameter vector, which can represent the weights of a neural network or any other parameters that we are trying to tune in this machine learning model. So now for this objective function, the gradient descent, the vanilla gradient descent would look like this, where you start with some set of parameters wj and compute the gradient of this objective function. So the gradient takes this form of a sum of gradients of each of these individual loss functions. And then we apply this gradient to the parameter vector and update it. So the problem with just using this vanilla update is that if you try to compute the sum of individual gradients for a large training data set, that is, if capital N, that is the number of data points, is very large, then this is very expensive to evaluate and it's very time consuming, and that makes it almost intractable to directly use this algorithm in practice. And that is why what is used in practice is a different version of this, which is called mini batch gradient descent or mini batch SGD. And in mini batch SGD, what is done is that we make a small tweak to this gradient update. Instead of taking an average of the gradient over all the data points, we sample the data set, pick a batch of m data points uniformly at random, and then find the gradient only on those data points and take an average of them and apply. So the reason why this is SGD and not GD, the stochasticity comes from choosing these m data points randomly from the set. And mini batch represents this small batch size of size m. So as compared to batch gradient descent, which had a per iteration complexity of order of capital N, this has a per iteration complexity of order of m, which is much smaller if m is much smaller than capital N. But the disadvantage is that this is noisier than the batch gradient descent. Though in practice, this is the version that is used in most systems because it's tractable, and even though it considers noisy estimates of the full gradient, it works very well in practice. So the focus of this talk is going to be on mini batch SGD, the stochastic version of gradient descent. And mini batch SGD is not new. It is has been studied a lot in optimization theory and machine learning. In particular, there have been a lot of work on accelerating the convergence of mini batch SGD at a single computing node. So there are learning rate schedules like ADAGRAD, ADAM, momentum methods, variance reduction methods, second order methods, and so on. But the catch is that most of these methods have been designed for mini batch SGD when it is run at a single computing node. However, today we have enormous training data sets. So for example, ImageNet has 3 million something images, and training a model with such large data sets at a single node is almost impossible. So it has become imperative to scale SGD algorithms to a system of many computing nodes. And that is the focus of our work. So our aim is to improve the convergence of SGD when it is run in a distributed manner. And what do I mean by distributed? This computation that we had in the gradient update that we looked at before, where we are computing gradients at the different data points, we distribute that task of computing gradients across multiple computing nodes. And there are different ways of implementing distributed SGD. One common framework is a parameter server framework, which is shown over here on the left, where we have many workers who compute gradients and send them back to a central server, which then aggregates these gradients together and performs the parameter updates. So this is the model that's used in many real systems. Another model that is becoming increasingly popular, especially in edge computing systems or federated learning terms that you might have heard, is where these worker nodes, they not only compute gradients, but they also perform local updates. So you can think of an instance of SGD that's run at each of these computing nodes, and periodically they are talking to each other and trying to achieve consensus between the models. So our work looks at both of these frameworks, and the common theme is that we want to understand how the convergence of SGD is affected by system level issues, such as these worker nodes slowing down, or not having the same set of model parameters at which they are computing gradients, which causes gradient staleness. Also issues such as communication delays between the nodes. And the reason why considering these issues is important and how to couple them with SGD is that typically in optimization theory, people look at the convergence of SGD with respect to the number of iterations. So you will see error bounds of the form that to reach epsilon error, we will take order of these many iterations. But when you run SGD in this distributed manner, the time taken to complete each iteration can be very different for different architectures, depending upon how many workers you have, what are the communication delays in the system. The runtime per iteration can be very different, and that can completely change our perspective on the speed of convergence of SGD. So the approach that we take in our work is that instead of looking at the error convergence with respect to the number of iterations, we look at the convergence with respect to the wall clock time. So in this example that I'm showing here, we are showing the error convergence with respect to iterations for two versions of SGD, synchronous and asynchronous. I'm going to describe in more detail what these versions mean. So as you can see, asynchronous is worse in terms of error than synchronous. But now if we change the x-axis to the wall clock time, where we consider the runtime per iteration of these algorithms, then we can see that the asynchronous SGD version, the curve gets compressed drastically. And it does much better than synchronous SGD, at least at the beginning. So initially, it has this sharp drop, and it converges very quickly. But then later on, it has a higher error floor than synchronous SGD. And these are the trade-offs that we are trying to understand. How can we find a sweet spot between these two? Can we get an algorithm that achieves a fast convergence in terms of wall clock time, as well as a low error floor at the end? Okay. And to approach the problem from this angle, we not only need novel convergence analysis, because even the convergence with respect to number of iterations has not been well understood in these distributed SGD settings. So we need novel convergence analysis, and also we want to couple it with runtime analysis as well as new scheduling schemes of how to aggregate and apply updates. So this is the high-level theme of the talk. If there is one thing that you want to remember from my talk, the message is that we should look at SGD convergence with respect to wall clock time instead of number of iterations when SGD is run in a distributed setting. So going back to my previous slide about the two different frameworks, these are the two different parts of my talk. So first, let me go to the parameter server framework, where we'll compare synchronous and asynchronous SGD and their variants. So describing the parameter server framework more concretely, suppose you have P worker nodes. So these worker nodes are going to share the task of computing the gradients. And the parameter server holds the current version of this parameter vector W. Now in each iteration, the workers will read this W and compute gradients at this parameter vector for one mini batch of data. So the data is split across these different workers. These different workers have different parts of the data set. And in each iteration, they sample one mini batch of data from their subset and compute gradient of the parameter vector at that point. And now these gradients are aggregated by the parameter server and applied to get a new version of the parameter wn plus 1. So wn plus 1 is equal to the original w minus average of these gradients multiplied by some learning rate eta. So what are the advantages of doing this as compared to single node SGD? One main advantage is that since we have P worker nodes, we are processing P times more data in each iteration. So effectively, this is as if we have a P times larger mini batch. And it has been shown earlier that larger mini batch sizes give a better error performance at conversion. So the error floor that we saw, the horizontal part in the previous curve, is much lower if you have a larger mini-batch size. But on the other hand, the disadvantage of this framework is that if any one of these worker nodes slows down, then that can bottleneck the entire training process. So the runtime per iteration is determined by the slowest of these workers. And that's why, although synchronous SGD does well in terms of error versus iterations conversions, the runtime per iteration can be pretty bad as the number of workers go on increasing. And this is actually a big problem in cloud systems where the workers are run on shared resources. So the workers are run on some cloud servers that have background processes that are going on. And because of these background processes, there can be unpredictable fluctuations in the computing time taken to complete each iteration. If they run on high performance hardware, then this slowdown of workers is not so much of an issue. But in cloud systems, or even more in on-device machine learning, such as edge computing systems, this can be a big issue. So a solution to this problem of bottleneck of waiting for slow workers is to just do asynchronous SGD. In asynchronous SGD, what we do is we just remove the condition that the parameter server has to wait for all the workers in each iteration. What it can do is that as soon as any one worker responds with its gradient, so let's say worker 1 responds with the gradient of 1 mini batch, the parameter server just goes ahead and updates the central parameter vector. So now wn becomes wn plus 1 at the parameter server. But then this updated parameter is only given back to the worker which sent the gradient. All the other workers, they are still computing gradients on the older version of the parameters wn. And because of that, when one of them sends back a gradient, the parameter server can just apply it to the next update. But then this update is not absolutely correct, right? Because now the gradient is computed at a previous version of the parameters. This is wn, whereas the model that I'm updating is at wn plus 1. And this delay or this staleness in gradients can become arbitrarily large. In general, depending upon the relative delays of these workers, the index of the gradient that's computed can be some tau of n, which can be many steps behind n. And this tau of n is a random variable, which depends on the delays at these workers. So although asynchronous gradient descent just eliminates the problem of straggling workers because we don't have to wait for multiple workers to finish, it introduces this gradient staleness. And this staleness can increase the error and make the conversions worse. So the objective of our work was to understand these trade-offs between error and runtime and try to strike the best balance between synchronous and asynchronous SGD. And that's why what we did is we first looked at the error analysis. So we'll first discuss the error analysis of synchronous and asynchronous SGD, then do runtime analysis, and then put them together to see whether we can construct straggler mitigation strategies and staleness compensation strategies that give the best performance in terms of error versus runtime. Now let's go to the error analysis. Let me start with synchronous SGD. So if you recall, the update rule was as shown over here. And if we compare this to the update rule of mini batch SGD, it's actually exactly the same. It is equivalent to mini batch SGD, but with a batch size of PM, where P is the number of workers and M is the mini batch size. So we can actually directly use existing convergence analysis for C strongly convex and L Lipschitz smooth functions. There is a convergence analysis of mini batch SGD that's given in this work, and we can just directly extend it to synchronous SGD. So for synchronous SGD, the error in the model after j iterations. So the left-hand side gives the difference between the value of the objective function after j iterations and the optimal value. And the right-hand side gives the bound on the error. So the bound on the error has two terms that you should focus on. The first term is the error floor, which is asymptotically the error that we get. And the second term that you need to focus on is the decay rate. This is the rate at which the error is decaying. And what we can notice here is that as the number of workers P increases, the error floor goes down because the denominator of this error floor term is increasing. Whereas the decay rate does not depend on the number of workers or the mini batch size. The decay rate just depends on the strong convexity parameter of the function C. Now note that although I'm presenting the analysis here for strongly convex functions, this can be easily extended to non-convex objectives where we can show convergence to a stationary point. But I'm going to present it for strongly convex functions for now. Now this was synchronous SGD. It was just a simple extension. Now let's think about asynchronous SGD. So in asynchronous SGD, the update rule is different. It's given by this quantity where you have the tau n, that is a random variable. This is the gradient staleness term. And because of this gradient staleness, asynchronous SGD is actually very hard to analyze. There's not been much work on it. Very recently, there's been some works that have analyzed asynchronous SGD, but there are certain assumptions that you have to make on this gradient staleness in order to get a tractable convergence analysis. So some assumptions that are made in previous work include an upper bound on the staleness or a geometric staleness distribution or independently drawn gradient staleness. And in our work with Sangamitra, we have another convergence analysis which relaxes some of these assumptions. So we remove these assumptions and instead consider a weaker bound on the gradient staleness. What we assume is that the difference between a fresh gradient, which is nabla of FWJ, and a stale gradient is upper bounded by some factor gamma times the fresh gradient. And using this assumption, we are able to get a new SGD convergence analysis. The reason why this is possibly better is because we don't have a hard upper bound on staleness. This assumption allows tau to take an arbitrary distribution, which can take infinitely high values with low probability. And we do not assume independently drawn staleness or a specific geometric staleness distribution. Now, with this assumption, we can get the following convergence result or upper bound on the error. So this is similar to what we saw before for synchronous SGD, but some terms are different. So let's try to tease out and focus on those terms and see how they compare with synchronous SGD. Now let's look at the first term. This is the error floor. This is typically larger than synchronous SGD. If you recall earlier, instead of this gamma prime, which is now 1 minus gamma plus some quantity, we earlier had T over here. So the error floor is worse than synchronous SGD. But the decay rate now includes this gamma prime term, which depends on the staleness. And interestingly, this decay rate could be either faster than synchronous SGD or slower. And this is just in terms of number of iterations. I have not even introduced the runtime benefit. So interestingly, asynchronous SGD can actually be faster even in terms of error per iteration. And the reason behind it is because these gradient staleness terms add some sort of momentum to the algorithm. And because of this added momentum, as long as it's small enough, we can get faster convergence in asynchronous SGD. But that depends on the staleness distribution and how much momentum is added. In in the worst case, asynchronous SGD can also be slower than synchronous SGD. It just depends on the delay distribution. So now putting these together with the runtime analysis, let's look at the runtime analysis and see how asynchronous and synchronous SGD compare. Now, if we try to find the expected runtime per iteration, assuming that, let's say, each worker takes an exponential amount of time to finish its gradient computation. Although I'm presenting the results for exponential service times here, they can be generalized to any service time distribution. Now, for synchronous SGD, the time taken to complete each iteration is determined by the slowest worker, right? So that's why it's the expected value of the maximum of p exponential random variables, which scales roughly as a log p. And that implies that as the number of workers increase, our runtime per iteration is going to increase logarithmically. Now, if we compare this with asynchronous SGD, where we don't have to wait for all the workers to finish, we can show using some renewal theory analysis that the runtime per iteration is actually 1 over mu p. And interestingly, now you see that this is p log p times smaller. Here, as we add more workers, the runtime per iteration actually gets smaller and smaller, whereas in synchronous SGD, the runtime became worse as we added more workers. And this means that clearly asynchronous SGD is winning in terms of runtime per iteration. Now, putting these together, we get the plot that I showed at the beginning of the presentation, where if we compare synchronous and asynchronous SGD with respect to the wall clock time instead of the number of iterations, we get that asynchronous SGD, because of its small runtime per iteration, has a sharp drop in the error at the beginning, but then later on, it converges to a larger error flow. And for this example, we could show that asynchronous SGD actually takes 5x less time to reach the same training loss. And these are theoretical results, but even in experiments, we can see large gains in asynchronous SGD over synchronous SGD. Now, the next thing that we want to do is, so far we looked at these two extremes, synchronous and asynchronous. Can we do some?
I have a quick question here. I don't know if it's important, but does the step size matter here? Did you take fixed step size, or do you have anything to say about the step size here?
Yes, that's a good question. So far, we have considered fixed step size in the analysis.
Okay. It doesn't matter? Is this something one should worry about, or it's just...
So in general, in practice, what is used is varying step size, and the insights are very similar. The analysis becomes much harder if you have varying step size, but because we are looking at the error versus wall clock time convergence here, the advantage that we get in terms of runtime will be very similar in even if you have a varying step size.
Okay, thank you.
But the analysis is for fixed step size. Thanks for pointing that out.
So I have a question here. So instead of waiting for everyone, if we wait for just, let's say, half of the people, and we can, then that will not have this log term, and probably the convergence will be faster. So what happens in that case?
That's a very good question. That's actually the next part that I'm going to talk about.
Okay.
Yeah, I'm going to come there. Any other questions? Okay, let me move on. So as one of you mentioned, these two algorithms seem a bit extreme, right? Either we are doing completely synchronous or completely asynchronous. Can we try something in between where we wait for a subset of the nodes to finish? And that is exactly what we are trying to do by designing SGD variants that have straggler mitigation properties. And it's a very simple change in these algorithms. So if you consider fully synchronous SGD, where you have this parameter server and the different workers, we were waiting for the slowest worker to finish in every iteration. So in these diagrams that I'm showing, the length of the arrow represents the time taken by the worker to compute gradients. And the vertical lines correspond to updates of the parameter vector. Now in fully synchronous SGD, we were waiting for the slowest worker to finish. And because of that, you have some workers, the fast workers, that is becoming idle. Now to avoid that, we can construct something called Async SGD, where we wait for any k workers to finish. Now, in the same model, suppose we wait for any 2 out of 3 workers to finish, then we can just cancel the third gradient and then update the central parameter. Similarly, we do that for the next steps. So as you can see, compared to fully synchronous SGD, K-sync is much better because it does not have to wait for the slowest worker. And by changing the value of K, you can control how many workers we wait for. But there is still some idle time that we observe over here. So you can see a white space between this arrow and the dotted line, which means that worker 2 is sitting idle while the second fastest worker is finishing. So we constructed a different variant, which is called K-batch sync, that actually eliminates this idle time. What we do over here is that instead of waiting for K workers, we wait for K mini batches to finish. What that means is that as soon as the fastest worker finishes its computation, it can just move on and start computing the gradient on a new mini batch at the same parameter vector W0. And as soon as any 2 mini batches finish, we just update the parameter vector W and cancel all outstanding gradient computations. So this method eliminates all idle time at workers, and it's much faster than both fully synchronous and K-synchronous SGD. And if we compare the runtime, I'll show it in the next slide. It cuts off this logarithmic term. As you mentioned, instead of a log K scaling, this has a log P divided by K scaling. And such methods are not new, so we are not the first to design these methods. These have been observed in revisiting distributed SGD by Google and other algorithms. But I want to note that what we are doing here is different from erasure coding techniques. Some of you might think of gradient coding, which has a similar idea that you're trying to mitigate the stragglers or waiting for slow workers. Here, instead of using any coding, we are just ignoring the slow gradients. And that is generally fine because data has a lot of redundancy already. So as long as this data set is well shuffled and there is enough number of data points at each worker, it is okay to ignore slow gradients. We do not need to use erasure coding. Erasure coding can be useful in the case where you have small amount of data and you cannot afford to ignore slow gradients. So that is the distinction between this and gradient coding techniques.
So Gauri, I have a question here. So it's exactly what it is. So do you assume that the data is replicated on all the servers or all the workers, or?
No, we do not assume that the data is replicated. You have a data set that is split across different workers.
But you have to reshuffle every iteration?
No, you're not reshuffling after every iteration. We are not considering reshuffling specifically.
Oh, okay.
So in each iteration, the worker samples a mini batch of data and then just uses that for the gradient update.
And in your implementation, so this sampling is independent. So in each iteration, you think different servers are going to be stragglers, or independent across iterations?
Yes, at least for the analysis, we are assuming that it is IID across iterations and across workers. But in practice, it may not be like that. Right.
I also have a question about the K-batch sync SGD.
Mm-hmm.
So at some point, worker 2 was working with W1, whereas worker 1 and worker 2 are still working on W0. Isn't this some kind of async, or?
Yes, that's a good question. It's not async. because we are canceling the slow gradients, every time the central parameter is updated, so when you go from W0 to W1, all the workers now start computing gradients at W1.
Oh, okay.
So it is not asynchronous in the sense that you have some workers computing gradients at W0 and some workers computing gradients at W1 at the same time. That doesn't happen.
Okay. So based on the graph, so if when worker 2 finishes its first mini batch, it starts, so is the W updated at this point?
Can you repeat the question? Sorry.
So for worker 2, when worker 2 finishes up based on the first mini batch, so starts updating again based on a second mini batch. That's what the graph is showing. Right?
Yes, yeah, it starts updating.
Yeah, but at this point, the W of the whole system doesn't look to be updated, or it is.
Yes, exactly. So we don't update the W. The worker computes a new gradient at the same W.
Oh, okay. Then when you have 2, you stop everyone, right?
Yes, you stop everyone. So
Okay.
this does need some increased coordination between the parameter server and the workers. But it is still synchronous SGD.
Okay, thank you.
I have a question here. So
Yes,
you
go
assume that, thank you. So you assume that worker 2 has more than one batch, right? So for instance, worker 2 could have 3 mini batches, 4 mini batches.
Mm-hmm.
And so the mini batch, is it one point or is it like a subset?
Okay. So mini batch is typically, let's say each worker has 10,000 data points or 10,000 samples. Then a mini batch is typically either like 64, 128. That is the typical mini batch sizes that are used in practice.
Okay.
So each worker has many mini batches of data in its memory.
Mm-hmm. Mm-hmm. Okay, and does not use them all. It use them
Yeah, it does not use them all in each iteration. In each iteration, it's going to sample one small mini batch and use that.
Okay. Thank you.
Any other questions? Okay, so let me move on. Now, some of you might have noticed that there is something wasteful about these algorithms. We are canceling these slow gradients, and that may not be possible in practice. It can actually involve additional signaling overhead. So instead of this, so this is my runtime slide. Let me actually just quickly go over that. You can see that K-batch synchronous SGD actually cuts out the log term completely. Because we are not waiting for multiple workers to finish, it does not have any log term at all. And it's much faster than both fully synchronous and K-synchronous. Now with that, let me talk about choosing the best K. So if you plot the error versus runtime convergence for different values of K, this is for the MNIST dataset, we can see that as K increases, that is, we are waiting for more and more workers, the plot becomes more stable, or it does not have as much noise. And the reason behind that is because the effective mini batch size that we have increases. So we have less noise in the gradients. But as you increase K, the runtime per iteration increases, and that's why it is slower in terms of convergence. So for this example, K equal to 4 strikes a good trade-off between convergence speed and error floor, and maybe that's the right value to choose for this particular example.
And what was the total number of workers here?
The total number of workers is 8,
Okay.
I believe. Yeah. Yeah, it's 8. Okay, so this was for synchronous SGD, but as I said before, instead of canceling these slow gradients, what if we just make use of all of them? So in asynchronous SGD, the pure fully asynchronous version that I described before, the parameter server waits for any one gradient and updates and then moves on. And these slow workers are still computing gradient at an older version of the parameters. So there is a lot of gradient staleness that's going on in this figure. And now instead of making fully synchronous SGD less synchronous, what if we try to make asynchronous SGD more synchronous? So we can design a gradient variant which is called K asynchronous SGD, where instead of waiting for only one worker to finish, now the parameter server could wait for 2 gradients and only then update the central parameter. But now it does not cancel the remaining gradient, it just lets that worker do its job, and then as soon as the next 2 gradients come through, it will update the central parameter. So now the gradients can be a bit mismatched. So when we are going from W1 to W2, one of the gradients was actually at W0 and another one of the gradients is at W1. And that can happen. We just use these stale gradients. So the hope is that as K increases, the algorithm becomes more and more synchronous, so the gradient staleness reduces. And as you can see here again, we have an issue of some servers idling. And to avoid that, we can again do K batch async, where we wait for any K mini batches to come through, no matter which workers finish it. But we don't cancel the outstanding gradient. So in every iteration, we just wait for the next K mini batches to be finished, no matter which workers compute and send them across. And with this, we can now get very fast runtime per iteration, and our runtime and error analysis can actually be extended to these variants of asynchronous SGD. So putting all of this together, what we did is that we tried to span the spectrum of the error runtime trade-off by constructing these variants. So if you look at the error at convergence, note that this is at convergence. This is the asymptotic error flow that I get, and the error and the runtime. Then asynchronous SGD is over here. It has high error flow at convergence, but very small runtime per iteration, whereas fully synchronous SGD is here. And by changing the value of K, we can achieve different points on this trade-off. And by going to batch async or batch sync SGD, we can also get another curve, which is different. And depending upon the delays in the system, we can choose a suitable value of K on this trade-off. So ongoing research direction that we are pursuing is to try to strike the best trade-off between async and sync by maybe starting with asynchronous SGD and then slowly increasing the value of K to reach the error floor, the low error floor that is given by synchronous SGD. And this is something we are still exploring. I'll show a similar result that we have for communication efficient SGD, where we actually do this adaptive change in the communication scheme. But for this particular problem, this is still ongoing work. Now let's actually go back and look at this trade-off and look at asynchronous SGD. Asynchronous SGD is clearly winning in terms of runtime. You cannot do any better than that. But error at convergence was worse in asynchronous SGD because of this staleness that was occurring in the gradients. So let me try to actually address that directly. What if we can change the update in such a way that we reduce the staleness in the gradients without affecting the runtime? And that is something we tried by changing the gradient update. So we proposed a learning rate schedule. This learning rate schedule can be used on top of other learning rate schedules such as AdaGrad or Adam. Here what we're doing is that whenever an update is really stale, so whenever wj is very different from w tau j, that is the stale update, then we apply a smaller learning rate to the gradient update. So it's a small tweak in the learning rate, and this actually allows us to remove that bounded staleness assumption in our analysis. And in practice, if we use this kind of learning rate, then we can get much better convergence. So here I'm plotting the error versus number of iterations for the fixed learning rate, which is shown in blue. And the orange curve shows this variable learning rate with the same eta max. So the eta max is fixed to 0.01 in both of these curves. And what we can observe is that by compensating for staleness using this strategy, you can actually get very stable convergence and a low error flow as well. And this idea is related to an idea of momentum tuning, which was proposed in this paper in 2016. However, the difference is that the momentum tuning idea was started off with the assumption that the staleness distribution is exponential, whereas this learning rate schedule works for any distribution of the delays in the worker nodes. So with that, I want to wrap up the first part of the talk. If you have any questions, I can take them at this point and then move on to the second part, which is on communication efficient SGD. Okay, no question. Salim, can I do a time check? How much time do I have?
Yeah, so maybe 15 more minutes. Is that sorry?
Okay,
Yeah.
So maybe the second part I'll go through it a little more.
Yeah, and
fast.
then maybe yeah, we'll keep our question till the end. I think.
Okay, sounds good. So far we looked at this parameter server framework where the workers were computing gradients and sending them back. But a big limitation of this framework is that it required constant communication between these worker nodes and the parameter server. So now I'm going to talk about a system where we try to reduce the communication between nodes. Because in edge computing systems where machine learning is increasingly being deployed, the communication between nodes can be very expensive and slow. So there are two different ways in which generally you can reduce communication, and these have been explored in recent works. One way is to compress or quantize the gradients sent by the nodes to the parameter server. So this reduces the amount of information that's sent to the central server, but then it does not reduce the number of times you send information. So the way you can reduce the frequency of communication is by having these nodes not only compute gradients, but actually perform local updates to the parameters. And then after every few iterations, we can average these locally trained models in order to encourage consensus and reach a common model of high accuracy. And our focus is on considering the second way of reducing communication, where each node is allowed to perform local updates. So let's dig deeper into that and try to see what are the parameters that are of interest over here if we try to do distributed SGD with local updates. So the first parameter is the number of local updates that you can do. So we denote that by tau. The second design parameter is the model averaging method. So as you can notice here, I'm showing this figure which does not have a central server. So the discussion that I am going to present over here can be applied with a central server as well, where each node performs tau local updates, or it can be applied in this decentralized fashion where nodes don't talk to a central server, but they just communicate with neighbors. And that is where the model averaging method comes in. So either you can have a simple averaging at a central node where after every tau iterations, tau local iterations, the models are just averaged together. And the new model, the averaged model, is sent back to all the nodes and they start computing the next set of tau updates using that model. But another averaging method is what is called elastic averaging, where instead of bringing all of these models to one common averaged model, we just move them closer to each other. And that is why it's called elastic. You can think of some spring that's attached between these models that's trying to pull them together and avoid them diverging and going in different directions. And another averaging method is just to eliminate the central server altogether and have decentralized averaging, where each node talks to its neighbors and averages its own model with the models at the neighbors. So all of these methods have been studied separately in different works, but in general, the error convergence analysis with these local update SGD algorithms is quite open, especially for non-convex objectives. There's not much work done on it, and there's a lot of room for improvement. So our approach is again to look at the error runtime trade-off in these local update SGD algorithms. So we want to look at the, instead of looking at training loss versus number of iterations, we want to change the x-axis and look at training loss versus wall clock time. And here the trade-off is that the less communication that we have between the nodes, so if we have more sparse averaging or if you have a large value of tau, then that reduces the communication delay, but it increases the discrepancies between these local models that can give worse conversions. So again, in the similar fashion, let me try to describe the error analysis and runtime analysis and then put them together. Now, the error analysis, for this, we use an interesting new framework, which is called the Cooperative SGD Framework. And at a high level, what this is doing is that this framework encompasses many of the existing algorithms. So the periodic averaging SGD, elastic averaging SGD, decentralized SGD, all become special cases of this framework. So once we get a convergence analysis with this, all of the other convergence analysis just follow as special cases of it. So the key elements over here are that you have these nodes that are storing different versions of the model. And we consider M workers, or these store P versions of the models, and V auxiliary nodes. So let me explain what I mean by auxiliary nodes and workers. In each iteration, the workers make local updates. So the M workers make tau local updates each. However, there are no updates made at the auxiliary nodes. And after these tau set of updates, there is a mixing matrix W. So this determines how the models are averaged. Either it can be a decentralized average where nodes are communicating only with neighbors, or a centralized SGD or elastic averaging. All of that can be captured within this mixing matrix. And we can write a general update rule as shown over here. So now with this framework, we can denote any algorithm by 3 parameters. The first parameter is the number of local updates. The second parameter is the mixing matrix W, which determines how the locally trained models are averaged. And V is these auxiliary nodes. So the auxiliary nodes do not perform any local updates, but they serve like intermediate nodes to average between different sets of local models. And as I said before, fully synchronous, periodic, averaging, elastic, they all become special cases of this general framework with different values that these 3 parameters take. And we can, in fact, even construct many more variants that have not been studied so far using this framework. So a main contribution is that we can actually get a convergence analysis of this cooperative SGD framework. And this is very general, it's for non-convex objectives. So the assumptions that we make for the analysis is that we assume Lipschitz smoothness, unbiased gradients, and some bounded variance in these stochastic gradients. And under these assumptions, this is the error bound that we can get. So first note that the left-hand side of the bound, now since we have these different models at different nodes, what we are trying to study is an average model. And we want this average model to be as close to optimal as possible. But since we have a non-convex objective function, there is no unique optimal. So instead of looking at f of uk minus f of uk star, we are considering the sum of the gradients over different steps. So k is the number of steps over here, and we take an average of those gradients. So this is the quantity of interest. And this is quite typical actually. In many analysis and consensus optimization, they look at this same quantity. And the error bound that we get on this average model is as shown over here. And there are two terms of interest in this error bound. The first term is this green color portion, which is just the fully synchronous SGD error. And the second term is the network error. So this is the error that we are getting. This is the additional error that we are getting because we are reducing the communication between these different nodes. And the parameters of the model, the W and the tau, all appear within this network error term. So more specifically, we have this zeta parameter, which is the spectral gap of the mixing matrix. And this zeta takes a larger value for sparser networks. And you can already see tau, which is the number of local updates appearing over here. The parameter V, which was the auxiliary nodes, did not appear, but that's actually incorporated in the effective learning rate, N effective. So if you plug this in, we can see that actually adding more auxiliary variables gives slower convergence, but a lower error flow. Because these auxiliary variables, they average models, but they do not perform any local updates. And we can, if we plot this network error term, we can see a nice trend as the network becomes more sparse and as the number of local updates increases. So for sparser networks, you have a larger error bound, whereas as you increase tau, the number of local updates, you also have a larger and larger error bound. And so now this analysis, the main contributions that fall out of this very general error analysis is that this provides the first analysis of elastic averaging SGD. So there has been a paper in 2015 that proposed this elastic averaging SGD algorithm, but there was no error analysis for non-convex objectives. So this is the first analysis for that. And it allows us to compare periodic and decentralized averaging and even combine them together in a decentralized periodic averaging sort of an algorithm. So now let me go to the runtime analysis. Here, we are just simply trying to understand the effect of reducing communication on the runtime. So in fully synchronous SGD, because we are waiting for the slowest node to finish, the runtime sort of looks like this, where this blue block in between represents the communication delay. So you have the local computation time, which can be random. That's why these arrows have different lengths. And we have the communication delay, which we denote by D. So as a result, the runtime per iteration becomes the expected maximum of these local computation time plus the expected value of the communication delay D. Now, if we compare this to a periodic averaging SGD algorithm, where we still have a central node, but now these workers are performing tau local updates and then communicating. So as you can already see, this reduces the communication delay per iteration. And if we compute the runtime, it's given by this quantity. So the second term, E of D, gets divided by tau, the number of local updates. So the communication delay gets amortized over tau slots. But the first term is actually also much better. So if you notice, earlier I had just YMM, so it was a maximum of M random variables. Now it is a maximum of Y bar, where Y bar is the average local computation time over tau updates. So because we are taking this average, the tail of each individual Y bars is smaller, and that's why doing periodic averaging SGD also naturally has a straggler mitigation effect. So if you plot the tail distribution of a synchronous SGD versus periodic averaging, we can see that the tail is sharply reduced. So the red color distribution gives the periodic averaging SGD, which has a much smaller tail than the original synchronous averaging SGD. And this analysis that I
Quick question here. So when you say synchronous SGD in a distributed way, what do you mean exactly?
You mean synchronous SGD?
Yeah. So when you're implementing it without a centralized server, so.
Okay. So this is with a centralized server actually.
Oh, centralized. Okay.
Yeah. Here I'm only comparing the cases where we have a centralized server. The difference between these two is that synchronous SGD averages every iteration, whereas periodic averaging averages after every 10 iterations.
Oh, and both of them are with the centralized server?
Yes, both of them are with the centralized server.
Oh, okay.
So periodic averaging SGD, you could actually implement it by a fully connected topology.
Okay.
But for the purpose of runtime analysis, we assume that there is a centralized server.
And then, is there a hit that you take on the error because of you're doing the red thing? You just
yes, we do take a hit on the error, and the previous analysis that I showed captures that.
Okay.
So the second term of error that I showed in the previous slide has this tau factor over there. So as tau increases, the error flow becomes worse.
Okay. Thanks.
Yeah. So this runtime analysis, I'm skipping it for the mixing matrix and auxiliary variable because this is actually non-trivial and it's still open. Now, combining these together, I think related to Salim's question, how much hit do we take in terms of the error by doing this kind of periodic averaging? So if we look at the error versus wall clock time, this red curve corresponds to having a large tau, which is more local updates. So initially you get a sharp drop in the error just like before, whereas you get a larger error flow at the end. And what we want to do next is we want to design some adaptive communication scheme that achieves a win-win in both of these. So initially it starts with less frequent averaging and then gradually starts averaging more frequently in order to reach a low error flow. So that is the last part of my talk, which is on adaptive communication strategies. So intuitively we get the idea, right? That we should start with a large value of tau and then slowly go on decreasing tau, or in other words, try to average more frequently. But then switching tau is quite non-trivial because you don't know when these curves cross each other and when you should switch in practice. So our approach is to use our error runtime analysis that I presented before to decide these switch points. So a simple way to do that is to use this error bound, and let's focus on the version of the error bound with the central server. So I'm setting this zeta equal to 0 because zeta was for the decentralized network topology. So if we focus on the error bound only with the tau parameter, then the way we can get the error runtime trade-off is to now change this k, which represented the number of iterations, to the wall clock time. So we know that the wall clock time is as shown over here. If we approximate it by a constant y and constant d, then we can express k in terms of capital T, where capital T is now the wall clock time. And if we substitute that in the error expression, this is the error bound that we get. So now we have an error at some time t, which is given by this quantity. And in order to find the optimal tau, we can just heuristic choice is to take the derivative of this error bound and set it to 0. So obviously this is not the true optimal because we are using the upper bound on the error and then taking a derivative of that. But this is a heuristic choice, and that is the strategy that we are proposing, and this is called the ADACOM strategy. So we choose to set the number of local updates as shown over here. But this update rule, which decreases with tau, cannot be directly used in practice because many of these parameters that we have in this expression, such as L, the Lipschitz constant, sigma, the variance of the gradients, and so on, are not known in many machine learning problems. So we change this update rule slightly and create these intervals of time and decide to switch tau only at that interval. So we do not change tau at every instant of time, but we change it after every few iterations. And to remove the effect of those Lipschitz constant, we can take a ratio of the starting tau, which is tau 0, with the new tau after L of these intervals of time, and that's given by this quantity. And the original tau, the starting tau, we can get it by grid search. So what I'm describing here are basically practical modifications that you do in order to get a usable update rule. And interestingly, this update rule can also be used with other runtime learning rate schedules such as AdaGrad and Adam. So you can just plug in the learning rate at different times into the schedule, and it works with that as well. And we tried experiments on this update rule in practice. So this adaptive communication strategy for ResNet and VGGNet. And it actually works really well in practice. So these are some experimental results for VGGNet. And what you can see over here is that this black color line, which represents this adaptive communication strategy, achieves the same error in 3x less time as compared to some fixed value of tau. And similarly, even if you have variable learning rate, we get similar large gains in terms of the runtime required to reach the same error floor. And for ResNet, we again get similar results. So I want to conclude since I'm running out of time. So the key takeaways is that we want to integrate error reduction and runtime reduction strategies in order to optimize the true convergence of SGD with respect to the wall clock time. And there are many interesting directions that are still open for future work, including asynchronous local update algorithms, considering non-IID data, model parallel SGD, and gradient compression, quantization, etc. So with that, I want to stop and I can take any questions.
Yeah, thank you, Gauri. So if anyone has questions, so they can just go ahead and ask questions. Maybe I'll start with one question. So the I think what we call the cooperative SGD. So this reminds me, where you have the matrix W. This reminds me a lot of the gossip algorithm kind of setting.
Mm-hmm. Yes, so there has been actually there's a rich set of literature on these consensus optimization algorithms, including gossip SGD, decentralized SGD, and so on. The difference, so the analysis tools are actually quite similar, what we use in our work. The difference is that we allow local updates at the nodes. So many of these gossip SGD algorithms, they do not have local updates, but in each step, you just directly communicate with a randomly chosen set of neighbors.
Okay. And usually, do you optimize the matrix, the mixing matrix W, or you don't care about this?
That is actually a open direction that we are trying to pursue. Okay. So far, we go with a fixed given mixing matrix, but there is a lot of room for designing a good mixing matrix in these kind of strategies.
Okay. Because it may depend on the graph also, right? I mean,
yeah, and you could actually even change the mixing matrix over time. You could start with a sparse topology and then go to a denser topology as time goes by.
Yes. Okay, so if anyone else has questions. If not, so I would like to thank you again, Gauri. This was a great talk. Thanks a lot.
Thank you so much for inviting.